Welcome back everyone. In today's video, we will start off with one of the sounding methods or otherwise called as penetration methods which are conducted in the field to explore the subsoil properties. Now the other, the main penetration test or sounding methods that we apply are standard penetration test, then there is static cone penetration test and dynamic cone penetration test. Now, in today's video, we will be studying in detail about the standard penetration test. Now, these tests are also called as penetration tests because the main principle that we apply here is we apply a sort of penetration into the soil profile and then we measure the resistance of the soil against that particular penetration. So that is why all the three methods are otherwise popularly known as soil penetration test. Okay, so let's begin with the standard penetration test in this video. Now let's start off with the standard penetration test. Now this is also a in situ test which is conducted on soils and it is mainly conducted for cohesionless soils. See, though we can conduct for cohesive soils as well, but it would not yield very reliable results for cohesive soils. So this standard penetration test is more suitable for cohesionless soils. And actually, the parameter that we obtain from this standard penetration test is called as a penetration number, and that is designated as capital N. Okay, so what we get for the soil by conducting this test is called as the penetration number, designated as capital N. Okay, and we basically measure, as the name suggests, we basically measure the resistance of the soil against the penetration which is applied. Okay, so to apply a penetration to the soil, we need some device, right? So that device which applies penetration to the soil is called as a penetrometer. Okay, so in the three different penetration tests, that is in standard penetration test, the static cone penetration test and dynamic cone penetration test, the penetrometer used will vary. Okay, now how this penetration number is useful for us in getting the soil properties is that several scientists and researchers have derived uh, correlations between the penetration number as well as other soil properties. Like for example, if we take the cohesionless soils, there are several correlations between the penetration number n and the angle of shearing resistance phi, as well as there is a correlation between the penetration number n and relative density of the soil. Okay, so this will give us an idea about the what type of soil is it, or in what state does it exist, whether it exists in a very loose state, or medium loose, or medium dense, or it is in a very dense state. So that sort of information can also be uh, acquired from these correlations which have been derived. Okay, so we'll see what are those correlations given by various scientists in the coming slides. But I'm just saying that this penetration number is quite useful to us because there are already existing correlations derived between penetration number and mostly the shear strength of soil. Okay, so in cases when you are not able to find shear strength of soil through laboratory methods, you can easily make use of these correlations which are already available, and you can find out the equivalent shear strength of soil for a particular value of n at a particular depth in the soil strata. Okay, so this is the overall picture of a standard penetration test. Now the main apparatus of the standard penetration test is shown in this figure. Now, as you can see there will be mainly there, this is a tripod arrangement. Okay, so you'll have a tripod, and as you can see, this is a manually operated apparatus. Okay, you have a rope pulley system here, and basically this rope pulley system is attached to a hammer. Okay, now the arrangement is such that this hammer is actually put over a guide pipe. Okay, so this what you see here, one second. So this is the guide pipe. Okay, so along the guide pipe the hammer can move. Okay, so when you are actually applying the blows to the soil by means of this hammer moves along the guide pipe. Okay, and this guide pipe is attached to a anvil. Okay, so it is also a small device, okay, which is attached to this guide pipe. Okay, and your hammer is made to move along this guide pipe when the blows are being applied by means of this rope pulley system. Okay, now to this anvil by means of coupling we can connect the drill rod. Okay, now drill rod, the length can be increased depending upon the depth up to at which you have to conduct the test. So depending on that, the drill rod length can be increased further. Okay, now this drill rod is attached to the anvil by means of a coupling. Okay, so uh, at this part you will have a coupling which is used to attach the drill rod with the anvil, and at the end of this drill rod, it's not that visible, there is a sampler which is attached. Okay, now that sampler which is used in standard penetration test is called as a standard split spoon sampler. Okay, now samplers are devices which are used to collect the soil samples from various depths. Okay, now there are various types of samplers which are used, but in standard penetration test what we use is the standard split spoon sampler. Okay, so the basic arrangement of the apparatus is that, see, this anvil plus guide pipe will be one system. Okay, and to that anvil with guide pipe, your drill rod will be attached by means of coupling. Okay, and at the bottom of the drill rod, your sampler, soil sampler, in this case it is the standard split spoon sampler that will be attached to the bottom of the drill rod. Okay, so here in this penetration test, the penetrometer device which is used is the standard split spoon sampler. Okay, and how we apply the penetration to the soil is that manually we will be lifting as well as dropping this hammer, and the hammer will be moving along the guide pipe during that lifting and dropping process, and this hammer will be uh, directly falling over this anvil. Okay, so due to that effect, this sampler along with the drill rod will be penetrated into your soil. Okay, and as you can see, uh, there is a bore hole which is dug in order to uh, penetrate this sampler into the soil. Okay, so the first thing that you do for conducting the standard penetration test is that you will dig a bore hole by means of any boring technique, and that bore hole diameter will be in the range of 100 to 150 mm. Okay, so after digging the bore hole up to the required depth where you need to conduct your standard penetration test, you will be taking out your boring apparatus, and then you will be lowering your standard penetration apparatus into the soil. Okay, and then at that depth where you need to conduct your standard penetration test or SPT, you will be keeping the sampler in touch with the bottom of the borehole. Okay, where you are planning to conduct the SPT test. Now then the next thing that you do is that you will start applying the hammer blows into the anvil. Okay, and that energy will be transferred into the drill rod and ultimately to your split spoon sampler, which will make it penetrate into the soil. Okay, so you just need to simultaneously lift and drop the hammer such that the hammer will fall into the anvil, and that energy will be transferred into your drill rod and ultimately to your split spoon sampler. Okay, and then at the required depth, this sampler will start penetrating into the soil and your test will be done. Okay, now let's see in detail what the actual procedure of standard penetration test is. This is the procedure, but we will see what are the specifications that we have to take care. So as I said, you have already seen the apparatus. We have a hammer which falls over the anvil. Okay, so during that dropping and lifting process, the hammer moves along the guide pipe which is attached to the anvil. Okay, and then that energy will be transferred from the anvil to the drill road and ultimately to your split spoon sampler. Okay, so here the borehole dimension says, 55 to 150 in diameter, or it can be like a borehole of 100 to 150 diameter as well. Okay, so anyway you need to dig a borehole first up to the desired depth where you have to conduct the SPT, and then you have to take out your boring equipment and then lower your SPT equipment to that depth. Okay, and then conduct the test and then again take out that SPT equipment. Okay, and then further if you want to conduct the test at some other deeper depth, you have to again dig the borehole to whatever depth you desire. Again take out the boring equipment, then lower your SPT equipment, keep it at the required depth and conduct the test. Okay, so this is how the procedure of SPT works in a borehole. Now there are certain specifications that you have to be thorough of for this test. Okay, because the hammer weight which is normally used is 65 kg. Okay, or in some cases it is 63.5 kg hammer which is used. See, there are different types of hammers which is used for SPT test. Okay, so the weight will slightly vary. Um, as well as the efficiency of the hammer will also vary. Okay, depending on the type of hammer which is used. Okay, so normally the hammer which is used for this test will be having a weight of 63.5 kg or 65 kg, and it will be having a free fall of 750 mm. Okay, so the free fall that should be kept for the hammer is, there is a height through which the hammer should fall is 750 mm. Okay, to drive the sampler. Okay, so these are two specifications that you have to keep in mind. That is the weight of the hammer as well as the height through which the hammer has to fall, or the free fall height. Okay. Now, as I said, at a particular depth, you will be keeping the sampler and you will be, due to the hammer blows, this sampler will be driven into your soil or penetrated into your soil. Okay. But there is a specific measurement that we have to follow here. Okay. So what we will be doing is, suppose at 1 meter if we are going to conduct the test. Okay. First what we will do is, we will penetrate the sampler up to 150 depth. Okay, that is, or 15 centimeter depth. Okay, first you will penetrate the sampler up to 150 depth. Okay, and that 150 is normally treated as the seating depth. Okay, then again, so basically to penetrate into the soil, you have to apply the hammer blows continuously. Okay, so for that 150 depth that you penetrated, you have to count the number of blows which was required to penetrate 150 into the soil. Okay, now usually that first 150 that you penetrate is considered as the seating depth. Okay, so normally you don't have to record it, but just keep in mind that during the penetration, first penetration also, you actually record it. Okay, but that is not what we will be using for calculating the penetration number. Now the first 150 penetration is over. Now again what do you do is, you will penetrate the sampler to further 150 Okay, now how much it has covered? 300 Okay, so for this next 150 also, you have to count the number of blows or the number of hammer blows required to penetrate the second 150 Okay, now again you have to go for the third 150 penetration. Okay, so again you have to count the number of blows required to penetrate the third 150 mm into the soil. So basically, as I said, the first 150 mm that you penetrated will be ignored because that will be considered as the number of blows required for the seating drive. Okay. Now, how much have you covered? You have covered 450 mm penetration into the soil. So in that 450 mm penetration, the first 150 mm penetration is considered as seating drive. Okay, so that blow count will not be accounted. Okay, now what you do is you will be counting the number of blows, or you will be recording the number of blows which was required for the next 300 mm of penetration. Okay, so in the total 450 mm penetration, the first 150 mm penetration will not be accounted. Okay, you will be actually recording the number of blows required, which was required to penetrate the next 300 mm, the remaining 300 mm penetration in the soil. Okay, now that number of blows which was required for the remaining 300 mm penetration of a soil will be recorded as the SPT value. Okay, or the standard penetration number N. Okay, so basically at whichever depth you are conducting the SPT test, you will be keeping the sampler in contact with that. If as I said, if you are going to conduct the test at 1 meter depth, you will be keeping the sampler in contact at that 1 meter bottom of the borehole, and then you will start applying the penetration by the hammer blows. Okay, so actually a total of 450 mm penetration is done in soil, but that is done stage by stage, that is as 150 mm, 150 mm and 150 mm. Okay, so you will not account the blow counts required for the first 150 mm. You will only be counting the blow counts which was required for the penetration of the remaining 300 mm in the soil at that particular depth. Okay, and that blow count is recorded as the standard penetration number N value. Okay, so at that depth, that is the N value. Okay, now this is the same procedure which will be followed at whatever required depth you will be conducting the SPT. Okay, so usually SPT is conducted at every 2 meters depth, or wherever you will see a change in soil stratum, at that depth you will conduct the SPT test, because your idea is to get the soil samples as well from the various depths. Okay, so if you are seeing a change in soil stratum, then definitely it would be much more suitable to conduct the test at the depth wherever there is a change in soil stratum, so that you can get all types of soil samples from beneath the ground surface. Okay, or otherwise you conduct, another criteria is that you will conduct at every 2 meters depth. Okay, so this is a standardized procedure by the ISI, and you can find the details of this in IS 2131 1986 standard penetration test. Okay, so there is an IS code for this test as well. Now, see, there should be some way to know that we cannot proceed with this test, right? So, we should know that when that refusal from the soil part is coming. So basically, these are the three criteria that we follow to understand that we have to halt the test, or we have to stop the test. Okay, so if for every, see, if for any 150 mm, so total, as I said, you are penetrating 450 mm deep into every soil stratum. Okay, and basically that is done in three stages, that 150 mm, 150 mm and 150 mm. Okay, and if so what you're doing is, for every 150 mm you are recording the number of hammer blows required, and that standard penetration number will be the number of blows which was required for the 300 mm penetration into the soil. Okay, the remaining 300, which doesn't include the first 150 mm. Okay, now you will have to halt the test or stop conducting the test if you actually get 50 blows for any 150 penetration. Okay, so that means it is a highly resistant soil, and you don't, there's no point of conducting the test. Okay, so that much 50 blows were required for just 150 penetration, means there is no use of further continuing the test and applying the blows. Okay, so you can just halt the test or stop the test there. Or the other criteria by which you can stop the test is that if you're getting 100 blows for 300 penetration. Okay, so either if you're getting 50 blows for any 150 penetration, or if you're getting 100 blows for 300 penetration, then even 10 successive blows also produced no advance. Okay, that is, even 10 successive blows also could not make any sort of penetration into the soil also. That means there is no point of continuing with the test. Okay, so these are the three criteria. So any of this criteria can be followed as per the field situation, so, or as per what you encounter with, and then you can stop conducting the standard penetration test. So in this penetration test, we use standard split spoon sampler as the penetrometer. Okay, so the benefit of using standard split spoon sampler here is that we'll be able to collect the soil samples as well from the required depth, or at the depth where you are conducting the test. Okay, so that is also one advantage that we have. So these are the basic, this is how your split spoon sampler will look like. It is a long cylindrical, hollow cylindrical uh, pipe like apparatus. Okay, anyway, we'll be studying about samplers in detail. Now these are the, see, the outer, this is the cutting edge. Okay, so this portion is the cutting edge of the sampler, which will help you in driving into the soil. Now this is the outer diameter is 51.8 and the inner diameter of the sampler is actually, this is the inner diameter. It is marked incorrectly. Okay. Inner diameter of the sample is 35 Okay. And this is the height which is shown. Okay. So basically, it's like a tube-like apparatus. Okay. So the soil sample will be, as you penetrate into the soil sample will be getting into this sample. Okay. Now, these are the specifications of the split spoon sampler. It's a thick-walled steel tube which is split lengthwise. Okay, so basically after collecting the sample, you can split this whole thing lengthwise. Okay, so like you can just imagine cutting a tube into two halves. Okay, longitudinally or lengthwise. Okay, so then you can just recover the sample like that as well. Okay, so you can split the entire apparatus lengthwise, and the sampler is also standardized by the ISI. Now, as I said, this sampler will be connected to your drill rod, and it will be penetrated into the soil by the blows of the hammer applied. Okay, now I said that we will be penetrating a total of 450 into whatever depth at which we are conducting. Okay, but how will we know that we are actually penetrating 150 or we have actually penetrated 150 or 300 or 450 into the soil? Now that is made sure by applying graduations of 150 300 and 400 in the drill rod. Okay, so you mark these graduations of 150 300 and 450 in the drill rod. Okay, so as that is covered, you will know, as that is penetrated into the soil, you will know how much you have actually covered. Okay, so basically the graduations are marked in the drill rod. Okay, and your sampler is attached to the bottom of the drill rod. So, um, so there are various correlations which are derived between the standard penetration number and other soil properties. Okay, so Terzaghi and Peck has given these correlations. Now for cohesionless soils, you will find these correlations. So here, if you can see, they have given the range of standard penetration numbers, and with this range, so if whatever depth, if you are getting a range, whatever standard penetration number has been recorded, and if you want to find out the equivalent relative density or phi value of the soil at that depth, you can use these correlations given in the table. Okay, and you will also know what is the condition of that soil at site. Okay, so this is how you make use of these correlations. You have relative density dr, you have the phi value, that is angle of shearing resistance of soil, and the condition of the soil as well. Now this is for cohesionless soils. Now for cohesive soils, this is the correlation that has been derived with n. So the n has been it has there is a correlation derived between the standard penetration number and QU, that is unconfined compressive strength of clay soils. Okay, and you will also know what will be the consistency of the soil for the equivalent n value that you get. But basically we don't use this correlations much, because as I said, from standard penetration number you don't get like very reliable values for cohesive soils. Okay, so for the same reason we would actually prefer some vein shear test to be conducted in cohesive soils for understanding the shear strength in a better way, or for getting more accurate values of shear strength of cohesive soils. Okay, it will be better to conduct vein shear test other than conducting standard penetration test. So basically this is a test, and obviously there will be many corrections to be applied to this test. Okay, so these are the basic corrections that we are applied. These are the there are many corrections which are applied. Okay, so these are the corrections. There is so as per IS 2131/1981, we have to, we cannot directly use, okay, especially you just saw the correlation table of n value with other soil properties. Okay, so you cannot use the n value that you directly got from the field observation. That is, this is the n value for this 300 mm penetration at this particular depth. No, that is the observed n value. Okay, so that n value cannot be directly applied in the design or in any other equation as well. Okay, basically you will have to correct that n value for various other corrections. Okay, one only after correcting the n value and finding out the corrected n value, you can apply that corrected n value in any equations or in any other correlations to find other soil properties. Okay, so these are the corrections which are mainly applied. You have hammer efficiency correction, drill road length correction, sampler correction, borehole diameter correction, dilatancy correction, overburden pressure correction. Okay, so one by one we will see what are these corrections. The first is hammer efficiency correction. Okay, so as I said, there are different types of hammers which can be used. Okay, for applying the blows to your penetrometer. Now these are the two ones normally used in USA. Okay, these are the generally, okay, you will find these two types of hammer. That is, it's called as a donut with 2 turns of manila rope on the cat head with hammer efficiency EH, that is 0.45. Then safety with 2 turns of manila rope on the cat head with hammer efficiency as follows. So there are, if it's a rope pulley or cat head, 0.7 to 0.8, trip or automatic hammer 0.8 to 1. So basically depending on the type of hammer that you are used, you will have to apply the hammer efficiency correction as mentioned here. Okay, EH. Hammer efficiency correction is denoted by EH. Okay. Now the next type of correction is drill road length correction. So see, the drill road length can be increased depending upon the depth up to which you have to go. Okay, so and basically, whatever length you use, that or the whatever drill roads that you use for driving the sampler, it should have sufficient stiffness. Okay, so depending upon the length, the correction factor would vary. So from the table, as you can see, if the drill road length is more than 10, then a correction factor CD of 1 has to be applied. and if the drill road length is in the range of 4 to 10, then this is the correction factor range which you have to apply. And if the drill road length is less than 4, then you will have to apply a drill road length correction factor CD of 0.75. Okay, so these correction factors for drill road length will vary with respect to the length of the drill road used for conducting the test. So here the next type of correction is sampler correction. See, sampler corrections are applied depending upon whether you are going to use a liner inside the sampler or you're not going to use a liner inside the sampler. So liners are basically provided inside the sampler to reduce the friction that the soil will experience while it is getting into your sampler. Okay, so mainly if you're going to use a sampler without a liner, then you have to apply a sampler correction CS of 1. Then if you're going to use a liner, I mean a sampler which has a liner inside, then you have to apply a sampler correction CS depending upon the type of soil you are encountering with. That is, if it is a dense sand or clay, then you have to use a sampler correction of 0.8. Then if it is loose sand, then you have to use a sampler correction of 0.9. Okay, so this is the sampler correction. This is how we apply the sampler correction to your N value. Now next is borehole diameter correction. See, usually your borehole diameter has to be certain fixed. Okay, if it is oversized diameter and all, what happens is that at each depth there will be release of in situ stresses. Okay, so that is why you have to, so based on the diameter, you have to apply a correction factor. So if the borehole diameter is 60 to 120 mm, you have to apply correction factor of 1. Then if 150 mm diameter borehole, then 1.05 correction factor has to be applied. Then if it is a 200 mm diameter borehole, then 1.15 is the correction factor to be applied to your N value. Now, one of the most important corrections and most common corrections that we apply to the observed N value from the field test is that overburden pressure correction. Okay, now overburden pressure means the pressure or the confining pressure that is existing at each depth of the soil. Okay, which basically depends upon the depth and the unit weight of the soil. Okay, so at various depths, these overburden pressure or confining pressures will be different. Okay, and what really happens is that we sometimes tend to underestimate and overestimate these confining pressures at shallow depth as well as deeper depths as well. Okay, so in order to standardize the N value to a standard confining pressure, we apply a overburden pressure correction to this observed N value. Okay, now there are many equations given by different scientists for applying a suitable overburden pressure correction. Okay, so this is just one of the equations that we are using. So normally how we find the corrected N value is that, we will apply a correction factor Cn to this observed N value. Okay, so if N is the N value that you observed in the field, now you will multiply that N value with the correction factor Cn to get the corrected value of N for overburden pressure. Okay, now these correction factors which are applied, there are several equations for finding those correction factor. So here I have just one of those equations, okay, which is recommended by Peck, Hansen and Thornburn. Okay, this is not just one equation. There are many other equations that you can use as well. Okay, so one of the equations given by Peck, Hansen and Thornburn is that correction factor Cn is equal to 0.77 into log 10 of 2000 by P. Now P is the effective overburden pressure at whichever depth you are finding out. Okay, and that is in kilonewton per meter square. So first thing you have to find out this correction factor. That correction factor multiplied by the observed N value will be your corrected N value. Okay, so this is how you apply for overburden pressure and find out the corrected N value. Now another correction which is applied just after applying the overburden correction for soils is that it is dilatancy correction. Now this dilatancy correction is exclusively for uh, silty fine sands and fine sands. Okay, basically sandy soils or silty sands. This dilatancy correction is not applicable for cohesive soils, clayey soils. Okay, dilatancy or the expansion in volume, it is mostly prominent. It is prominent in the silty fine sands or fine sands. Now, the best example for dilatancy is that, when you step on the beach sand, and what really happens, the sand immediately under your feet gets compressed or compacted, and then you can see that the neighboring the sand around your feet gets dried up very quickly. Okay, so what really happens is that when you're compressing the sand under your feet, the water particle from the nearby that is from nearby around your foot area, in the sand around your foot area, will move into these uh, compacted sand under your feet and fill up the spaces. Okay, so this is what really happens in dilatancy. There is an expansion volume which is happening. Okay, and this is prominently seen in silty fine sands and fine sands. Okay, and we have to normally apply a correction for dilatancy when we are conducting test SPT test on such soils. Okay, and we will apply the dilatancy correction only if the corrected N value, that is the N value which is corrected for overburden pressure, exceeds 15. Only then we will apply dilatancy correction. Okay, so the two conditions under which we have to apply dilatancy correction is that, first you have to see whether the soil is a silty fine sand or a fine sand. Okay, and next what you have to see is that after applying for overburden pressure, if the corrected N value exceeds 15, then definitely you have to apply dilatancy correction. Okay, if it doesn't exceeds 15, then no issue, we don't have to apply for dilatancy correction. And remember, this correction is applied only for silty fine sands and fine sands and not for clayey soils. Okay, because we find these dilatancy phenomena only in such soils. Okay, so if your N value corrected for overburden pressure exceeds 15, then this is the equation that you have to apply to get the N value corrected for dilatancy. Okay, so if NC is the N value corrected for overburden pressure, then, and if that is greater than 15, then use this equation, that is 15 plus 0.5 into NC minus 15 to get the N value corrected for dilatancy. Okay, so dilatancy correction always follows your overburden correction. Okay, so these are the different corrections that we normally apply to N value, that is the observed N values, to get the corrected N value. So once we get the corrected N value, we can use that corrected N value in all the IS code equations and get the required soil parameters, as well as we can apply the corrected N values in the correlation tables and get the required other soil properties. Okay, so only corrected N values are used in the design finally. Okay, and not the observed N values. Now this flow diagram here shows you the sequence in which you have to apply the corrections to the observed N value. Okay, or the N value that you have measured directly from the field test at various depths. Now we have seen that there are many corrections to be applied to N, like hammer efficiency correction, there is borehole diameter correction, there is sampler correction, drill road length correction, then there is our overburden pressure correction and dilatancy correction. So these are the different corrections, but how do we know in what sequence to be applied? Okay, so your questions can be, sometimes your question will be very simple. Okay, it might be asking only for, see, normally or mostly it will be asking only for correcting the n value for overburden pressure. Okay, and if the soil given is the silty sand or fine sand, then you will, and if the corrected n value for overburden pressure exceeds 15, then you have to go for dilatancy corrections as well. Okay, so normally these overburden pressure and dilatancy corrections would be enough. Okay, but then if other correction parameters like drill rod length correction or sampler correction or hammer efficiency corrections, those parameters are also given in the question, then you will have to follow this sequence which is shown in this flow diagram. Okay, so normally you will be measuring the you or what you will be having is the field n value that you have measured directly from the field test. Okay, and now that you are going to correct that n value for various corrections that we just uh, saw. Okay, so normally we will denote that n value corrected as N60. Okay, here NO denotes the measured N value at field or the observed value of N at field. Okay, and if in the question you are given information regarding hammer efficiency or drill rod length correction, or CS is the sampler liner correction, or CB is the bore hole diameter correction, then you will have to go in the sequence itself. Okay, so this will be the first correction you have to apply to your observed n value if these parameters are also given to you. Okay, so here that n corrected n value is represented as N60. Okay, so N60, in N60, 60 means 60 is the percentage theoretical free fall hammer energy. Okay, now there are as I mentioned before, there are different types of hammers which are used for conducting the test. So in order to account for the variability in the efficiencies of different hammers used, we standardize the n value to 60% of the theoretical free fall hammer energy. Okay, so that is why we call that corrected n value as N60. Okay, which is corrected for EH, that is hammer efficiency, drill rod length correction, sampler correction, as well as bore hole diameter correction. So this many into your observed n value will give you the first corrected value for n, and it is denoted as N60. Okay, so N60 denotes that that is your n value has been standardized to 60% of theoretical free fall hammer energy. Okay, now once you have applied these corrections, okay, so only if in the question other correction factors are mentioned, only then you have to apply these to find out the first corrected n value. Okay, otherwise you can directly go to your overburden pressure. Okay, so if you have got N60 by applying this equation and by applying the other correction factors to the observed n value, then you have to move on to the next set of corrections. Okay, so now only two corrections are remaining, that is overburden pressure correction and dilatancy correction. Okay, so the first thing that you have to see is that whether it's a cohesionless soil or a cohesive soil. Okay, so this overburden pressure correction is applicable to all types of soils. Okay, because that every soil will have a overburden pressure at various depth, I mean, which will increase with increase in depth. Okay, so you have to apply the overburden correction to all types of soils. Okay, so after applying N60 correction, sorry, after finding out N60 corrected value, then you will have to see whether it's cohesionless or cohesive. If it's cohesive, then directly apply the overburden pressure correction. How to apply the overburden pressure correction? That will be this equation. Okay, so we know that the overburden pressure correction equation is, you have to find a correction factor for overburden pressure Cn. Okay, that into N60. So this N60 will be the one which you found in the preceding um, step. Okay, so this N60 was found by applying all the other correction factors to the observed N value. Okay, so the correction factor for overburden pressure into the N60 found in this step will give you the N60 dash. I have just denoted it as N60 dash, which is the N value corrected for overburden pressure. Okay, Now, for corrosive soils, you can correct the, you can stop the corrections with this step. Okay, you don't have to further proceed to dilatancy correction, because dilatancy is not a phenomena which is observed in corrosive soils. Okay, so for corrosive soils, this will be the last correction, that is overburden pressure correction. Now let's see what happens to cohesionless soils. If cohesionless soils also, you will have to apply overburden pressure correction using the same equation. Okay. Now after applying for cohesionless soils, you have to see two things: whether your N60 dash is greater than 15 or not. That is one thing which you have to see. And the other thing is that whether your soil is fine silty sand or silty sand below water table. Okay. Then if these two conditions are met after applying for overburden pressure correction in cohesionless soils, then you need to apply the dilatancy corrections. Okay. So after applying for overburden pressure correction in cohesionless soils, if these two criteria are met, then you have to go for your dilatancy correction. Okay. And dilatancy correction can be found out using the equation which I showed you under dilatancy correction. Okay. Now that marks the end of all corrections for cohesionless soils. Okay. So this is the sequence which has to be followed in applying corrections to your N value.